Okay, in this segment we're going to look at some translinear circuits. Involving that 4-transistor translinear loop that we analyzed in the last segment. Okay, so our first one is going to look like this. Okay, so we have 4 transistors here, and we can call them Q1, Q2, Q3, and Q4. And we've labeled the collector current, which is our output of the circuit here, IZ. And we're going to assume, we can call this V out, let's say. We're going to assume, in addition to the assumptions we made earlier about the matching and the same temperature, we're going to assume that V out is connected to something that holds it high enough that Q4 is forward active or in soft saturation. So that the forward active model applies. This is sort of like what we had with the current mirror. If we have the output voltage is at least a VCE sat above ground, and that means that the forward active model will apply to Q4 by hypothesis. And so now the question is, do we see this 4-transistor translinear loop that we analyzed last time here? Well, here we start if we start at ground, we go up 1 base emitter drop, and then we are at another emitter through this diode connection to a second base emitter drop here. It's a rise actually, emitter to base, so that matches up with what we had. And then we see Q3, base first, and we go down to the emitter, and we go down to the emitter of Q4. So we do have that same translinear loop that's embedded in the circuit. We go from ground up to base emitter voltage rises, and then we go down to base emitter drops. And so we have the same sort of arrangement, and so the same conclusion should apply, assuming that our forward active constraints are met by these other 3 transistors. We're given the 4th one by hypothesis. So let's think about whether these 3 transistors are going to operate in the active mode. Well, we've got Q1 and Q2 are diode connected. And so assuming they are carrying a current, the base emitter junction must be forward biased. Okay, and because the collector is shorted to the base in the diode connection, then the collector base junction is by definition reverse biased, because we've lumped in the VCB equals 0 case as being formally in reverse bias territory. And so Q1 and Q2 are diode connected and so are in the forward active region. So Q1 are forward active, let's say, because they're diode connected. Well, what about Q3? Well, Q3 is basically an emitter follower. Right? So Q3 has effectively a bias current of IY and is serving as sort of an emitter follower if you think about it. The voltage here at the input is something, 2 VBEs above ground, basically 2 diode voltages above ground, and the output is down here, basically 1 diode drop above ground. And so this transistor we've met before. We've met the diode connected transistor before. Now we've also met this emitter follower with a current source bias before. And we have some idea of what it's going to do, but we decided that as long as the input voltage is within the power supply rails, so it's going to be less than VCC, then since the collector is held at VCC, Q3 will also be in the forward active mode, assuming it's carrying a current. Okay, so Q3 is an emitter follower. And so it's forward active too. VC is greater than VB. So all 4 transistors are going to be operating in the forward active mode, which is good. So we can apply the translinear principle. So the translinear principle tells us that the product of these two collector currents will equal the product of these 2 collector currents. So we have to figure out what are the collector currents. Well, what's the collector current going to be in Q2? Well, what's up here? Well, IX is being forced into this diode connected transistor. By hypothesis, the base current of Q3 is 0, so the only place for this current to go is through Q2. So that must be basically the collector current of Q2. So IX is the collector current of Q2. That current flows out of the emitter of Q2 and flows into Q1, because these are connected in series with each other. So this current should also be IX. Well, what about Q3? Well, Q3, we're pulling IY out of the emitter of Q3, and we're assuming, again, the base currents are basically 0 in our idealized transistor assumption. And so the only place for that current IY to come from is the emitter of Q3, and that also must come from the collector of Q3 and from the power supply ultimately. And so we know the collector currents now, so the translinear principle says the product of IX times IX, or IX squared, is equal to the product of IY times IZ. Well, the output of the circuit is IZ, right? So what we would like is we'd like a relationship between the output current and the input currents, and we can get an explicit expression by solving this equation for IZ. That's what the circuit does for us in some sense. And we would find that IZ is equal to IX squared over IY. So what this circuit does is it implements a squaring relationship or a reciprocal relationship. So if I were to put in, let's say, 1 milliamp for IY, and I put in 2 milliamps for IX, the output should be 4 milliamps. So we have this very simple circuit involving 4 transistors that can implement this kind of interesting nonlinear relationship. And it's the kind of thing that we might be interested in doing, for instance, if we wanted to calculate the power or something like that in a signal that's represented by a current. We could square it. We might want to divide by something to normalize one thing by another to normalize it. And so this type of circuit has been used for real-time sort of analog computation of these kinds of nonlinear operations that we might need to perform on signals that are moving very, very fast, or maybe with very, very low power consumption. So that's our first example. For our second example, we're going to do something it's a little awkward here, but we'll hopefully illustrate something. So I'm going to take the same exact circuit and move the Q3 down here a little bit. And what I'm going to do is, instead of connecting the circuit up that way, I'm going to take my diode connection, which was over here on Q2, and I'm going to take it and I'm going to hook it up over here. And I'm going to make IZ my input current, and I'm going to make IX my output current. And we'll call this V out. And we're going to then change this assumption here that Q2 is held in the active mode. Okay? So here, we basically just taken our IX input current, and we've taken that and eliminated it, and we've put in instead an IZ input current over here. And we still have our IY current down here. And now we're basically saying that Q2 is going to be our output transistor. And we're guaranteeing that V out is going to be sufficiently high that Q2 is guaranteed to be in soft saturation, so that, or forward active. So that means either V out is basically at least VCE above whatever this node voltage is here. So this is going to be one diode drop above ground, or so, right? There's one base emitter voltage here, which is kind of in the range of like 0.4 to like 0.8 or 0.7, something like that. So as long as V out is at least, let's say, 0.85 volts or higher, then Q2 would be in soft saturation at least. If V out were greater than this voltage here, which is characterized by basically two diode drops above ground, which might be in the range of, let's say, 0.8 to 1.7 or 1.4, 0.7 times 2. So if the normal range for a bipolar transistor to sweep out its entire useful current range is, let's say, 0.4 to 0.7, then each of these could be in the range of 0.4 to 0.7. And so you'd have 0.4 plus 0.4 at the bottom end, and then maybe 0.7 plus 0.7 at the top end, which would give you a range of 0.4, I'd say 0.8 to 1.4 for the voltage here on the base of Q2/Q3. So we've taken that point and we've basically connected it to the collector of Q4. And that's kind of like a diode connection. it's not a direct diode connection, but it is a diode connection through Q3, which we just said was like an emitter follower. And so just like the beta helper transistor, when we talked about the current mirror, we could make the diode connection through a buffer, and modulo the level shift, it will do the same thing. And it doesn't really matter that there's the level shift there, because if this current is too big and this current needs to come up, what will happen is that this voltage will start to increase. That pulls up on the emitter, follows what the base is doing. It pulls up on the base of Q4 and turns the current level up, so that the difference between the input current and this current in Q4 is reduced. And so the negative feedback loop is preserved through this extra stage of amplification here, or this buffering stage. So we can do that, and IZ will be accepted by Q4 as the input current, and this feedback loop here will figure out what voltage do we need on the base of Q4 for Q4 to accept IZ. Okay, so that works just fine. And so the question is, have we changed anything about how these transistors operate? So Q1 is still diode connected, and so Q1 is forward active because it's diode connected. Q2 is forward active by hypothesis. Q3 is still an emitter follower. And the collector is tied up to VCC, which is the most positive potential. So VC is greater than VB strictly. What about Q4? And so Q4 is not diode connected, but can we say something about the relationship between the collector voltage and the base voltage here? Well, the collector voltage, because of the way we've connected this, is also the base voltage of Q3, right? So V3, so VBC, now let's say VCB, no, let's say, how do I want to label this? Well, V3 is greater than 0 because Q3 is in the forward active mode and it's carrying a current. And that means that the collector, Q4's, it's going to be easier if I just label these. So let me call this VZ and VY. That implies that VZ is strictly greater than VY, because V3 is by KVL VZ minus VY. VZ minus VY is greater than 0, implies that VZ is greater than VY. So the collector is greater than the base, and so it's forward active. Okay, it's actually a whole diode drop, or 1 VBE, into the forward active mode beyond a diode connected transistor, which is just on the borderline. So, yay verily, all 3 devices are in the forward active mode. We still have the same translinear loop, because we really haven't changed the circuit at all, other than by flipping that diode connection around and changing what we're calling the input and what we're calling the output. And so the translinear principle just tells us the same thing as it told us before. It tells us that Ix squared is equal to Iy times Iz. But now the circuit solves for Ix instead of Iz, because that's the output current. And so Ix would be equal to the square root of Iy Iz. So here we have basically a circuit that implements the geometric mean relationship. Between two currents, Ix and Iy. So the very same circuit, depending on how we where we choose to put the inputs and where we choose to put the feedback connections, can implement different relationships, and they're all sort of different based on the same translinear principal expression or the same translinear loop equation, just solving it for different variables. And in point of fact, we could make Iy the output if we wanted to, but that's not too different than having Iz be the output current, since the translinear constraint is symmetric with respect to Iy and Iz. In point of fact, the last circuit and this circuit are formally inverses of each other. They implement inverse functions of each other, and if you were to take the output of the one and feed it into the other one for the same value of the other current, you would just get a fancy current mirror. Wouldn't be a very good way of implementing a current mirror compared to the way that we talked about a couple of times ago, but that would give you sort of the identity function. Let's see. So that's our second example of something that you can do with this loop. The third example is going to be a little more interesting. So we're going to think about a circuit that looks a little more complicated. There's no dot there. And we're going to go into here. And then we have another transistor down here. And we've got two input currents here, which we'll call Ix and Iy. And our output current is going to be this current here, Iz. And here, instead of having just 4 transistors, we have 7 transistors. No, 9 transistors. No, I can count 7 transistors. And so the question is our familiar loop embedded here in the circuit? And the answer is yes, it is. It's in fact here twice. Okay, so here's one instance, and here is the second instance. So we have 2 instances of our translinear loop, same translinear loop, and maybe it would be better if I didn't make that path go that way, but maybe make it go that way. And so that's cool. We're going to also say that the output like before, I'm going to assume that V out is high enough to ensure the output transistors are forward active or in soft sat. And we're going to make our standard assumptions of all the transistors are operating at the same temperature and they are well matched and so on. So how about this case? This seems like a little daunting, but it's not too bad because these 5 transistors here are all diode connected. Okay, so these are all going to be operating in the forward active mode, assuming they're carrying a current, and the other 2 transistors are, by hypothesis, going to be operating in the active mode or in soft saturation. So we're all good with respect to the transistor's mode of operation for the translinear principle. And so now it's a matter of basically going through and figuring out what the collector currents are. Well, collector current here and here, since these 2 diode connected transistors are just connected in series directly to one of the inputs, are going to be IX. Likewise over here, these currents are going to both be IY. IZ is the total output current, and somehow IZ splits up between these 2 transistors, but then those 2 current components flow together and basically are the current flowing through this bottom transistor here. So the collector current down here is IZ again. The question is, what about these 2 output transistors? What will the currents be in these 2 transistors? When we're doing class in person, I usually ask people to think about that for a minute, so you might want to pause the video and give that a thought for a moment or two. But most people will say, well, maybe they're split 50-50. So this is half IZ and half IZ. And that's going to be true at one point. Okay, that's going to be true at the point where IX and IY are the same. When IX is the same as IY, then the voltage that I need for one of these transistors to produce IX is the same as this transistor to produce IY. And so 2 of those is going to equal 2 of those, and I'm going to have the same voltage here on each of these 2 BJT's bases. And since these are tied together at the emitter, they've got a common emitter node here, then the VBEs of these 2 transistors would be the same only at that point when IX is equal to IY. So in general, they don't split 50-50. The one that has the higher input current will actually have the higher base voltage here on its side than this, and since they have the same emitter voltage, will have the higher current. So the larger of these 2 things will basically, its transistors, the transistor on its side will get most of IZ, and the other one will get much less of IZ if one of them is significantly greater than the other one. But in general, we don't know what they are. So what we're going to do is we're going to call them IZ1 and IZ2, the first component of IZ and the second component of IZ. And so we know basically 3 things. We know from KCL, applied at the output node or applied here at this common emitter node, that IZ, the output current, is equal to IZ1 plus IZ2. And we know from the first translinear principle 1, we apply that around this loop, we know that Ix times Ix is equal to Iz1 times Iz. And we know from the second translinear principle equation that we have Iz times Iz2 is equal to Iy times Iy, or Iy squared is equal to Iz2 times Iz. So let's call this equation 1, equation 2, and equation 3. Well, 2, we can take equation 2 and solve it for Iz1. Just move the Iz downstairs and we find that that's equal to Ix squared over Iz. And we can likewise take equation 3 and solve it for Iz2 and find that Iz2 is Iy squared over Iz. If we call this equation, 4 and 5? We can take 4 and 5 and plug them into equation 1, our KCL, and we find that Iz is equal to Ix squared over Iz plus Iy squared over Iz. Now, we need to solve this equation for Iz because that's what the circuit's output is. That's what the circuit does. And so we can multiply both sides of this equation by Iz. And we have Iz squared is equal to Ix squared plus Iy squared. And we take the square root of both sides to solve for Iz. And we have Iz is the square root of Ix squared plus Iy squared. So the circuit actually has a name. The circuit is called the Pythagorator. I kid you not, that's actually what it's called in the literature. And it implements the Pythagorean theorem. So if you interpret Ix and Iy as the lengths of the legs of a right triangle, then the output of the circuit is the length of the hypotenuse. Or if Ix and Iy are the amplitudes of two sinusoidally varying current components, let's say, or signal components, then you have basically a circuit that takes the magnitude or computes the magnitude of that vector. So you can imagine Ix and Iy represent components of a communication signal, and you need to know what is the magnitude of the vector in some amplitude space. The circuit would do that for you in real time. So with 7 transistors, we can do this relatively complicated looking arithmetic operation, which involves taking a square root and taking the squares and summing them. And so that's pretty cool. Anyway, so that's it for this segment. In the next segment, we will take a look at one final example of this particular translinear loop, which I think is very interesting. And then we'll look at the effect of base currents. And we will see you next time.